The next topic of discussion is the Cisco proprietary protocol, Enhanced Interior Gateway Routing Protocol, or EIGRP for short. Now, EIGRP is an advanced distance vector routing protocol. Some books, especially the older ones, if you read them, it will say that EIGRP is a hybrid protocol, insinuating that it's partly distance vector and partly link state. That is absolutely incorrect. So that might have been a marketing ploy by Cisco to say that, okay, you get the best of both worlds, but that is not the case. EIGRP is a distance vector routing protocol. However, you can say that yes, it is an advanced distance vector routing protocol. Why is it an advanced distance vector routing protocol? Because EIGRP updates are non-periodic, partial, and bounded. So what do I mean by non-periodic? Well, with Route Information Protocol, the routing update, which was the whole routing table, was sent every 30 seconds. EIGRP does not send its updates every 30 seconds or every set interval. EIGRP only sends an update when something in the topology changes. A new router link comes up or a router link goes down. That's the only time an update is sent. The next word I used was the updates are partial, which means the contents of the whole routing table is not sent to my directly connected devices. Only the change in the network is sent, not the whole routing table. So if a link goes down, I'll let my neighboring router know that this link went down. I won't send the whole routing table over because that's not needed. Next, I said the updates are bounded. Bounded means the updates are sent only to neighboring devices that need them, not to everybody, which makes it more efficient. Hence, it is an advanced distance vector routing protocol. EIGRP updates are sent to the multicast address 224.0.0.10. Now, since updates are non-periodic, you don't know if your neighboring router went down at some point. So to counter that, EIGRP uses little packets called hello packets to keep the link alive and to discover directly connected devices. So if I receive EIGRP hello from a directly connected device, I know that device is alive. And I can discover that it's actually there. I have a neighbor that also speaks EIGRP. Now, within the hello packet is held the whole time for the neighbor. When I send a hello packet to an EIGRP neighbor, within it, I will set a hold time. The hold time is the number of seconds my neighbor is supposed to wait for me to send another hello or update packet before considering me down. The hold time is usually set to 3 times the hello interval. By default, the hold time is set to 3 times the hello interval. So, for link speeds greater than T1 speeds, which is 1544 kilobits per second, hellos are sent every 5 seconds. So the hold time for a link speed that is greater than 3 T1 speeds, the hold time will be 15 seconds, 3 times the hello interval. For link speeds less than T1 speeds, or less than 1544 kilobits per second, the hello timer is set to 30 seconds. So my hold time is 3 times 3 is 90 seconds. And my hello time would be 30 seconds. Moving on. EIGRP stores all routes to all destinations in a table called the topology table. So all routes are stored in the topology table. Even if multiple routes to the same destination, in case I have multiple links to the same destination present, even multiple routes to the same destination are stored in the topology table. Now these routes, as they sit in the topology table, are called feasible successor routes. One point, backing up for a minute, is all these routes are stored in the topology table, and the topology table exchange occurs after I have discovered my neighbors through the hello message. So when I send my neighboring router a hello, and I receive a hello back from my neighboring router, I will go ahead and exchange the contents of my topology table with my neighboring router, so that he learns all the routes too, or that it learns all the routes too. Now, as these routes sit in the topology table, they are called feasible successor routes. So these routes, as they reside in the topology table, They're called feasible successor routes. Each one of these routes has an associated metric, and the metric for EIGRP is called the feasible distance. I will go into more about how the metric for EIGRP works in about 5 minutes. But the metric for EIGRP is called feasible distance. Now, I said that all the routes to all the destination, even multiple routes to the same destination, are stored in the topology table. The best one of these routes, the best one of each of these routes, is plucked from the topology table and implanted in the IP routing table or your route information base, and then it is called the successor route. So which is the best route of all the routes in the topology table? Well, the best routes will be the one with the lowest metric or the lowest feasible distance. So the route with the lowest feasible distance is plucked from the topology table and implanted in the route information base or your routing table. And then it can be used. Now, EIGRP also has a concept called reported distance. Now, be advised that if you're reading a book on EIGRP, some of the older books call this the advertised distance. The newer books have now started calling it the reported distance. Now, what is the reported distance? The reported distance is the feasible distance for your upstream router. So what does that mean? Well, let's look at this topology. Router 1 is connected to router 2, and router 2 is connected to router 3. Network 10 at the very end is available to router 2 and router 1 through router 3. So, router 2 is a feasible distance of 50 away from network 10 or from router 3. So that is router 2's feasible distance. Now, router 2 reports a distance of 50 to router 1. So router 1 will see a reported distance of 50 because router 2 is reporting its own distance to router 1 as being 50. Router 1 will take that 50, and router 1 knows that its own distance from itself to router 2 is 100, and it will add the 50 to 100 to get a total feasible distance of 150. So, once again, a reported distance is the distance an upstream, or closer to the network, that we are trying to get to, an upstream router reports to you. So the feasible distance of the upstream router as reported to you. Now the next concept in EIGRP I'm going to cover is the feasibility condition. The feasibility condition says that a route's reported distance must be less than the route's feasible distance for it to be eligible to be installed in the topology table. So a route's reported distance must be less than the route's feasible distance for the route to be installed in the topology table. Let's see how this works. We have 3 routes between router 4 and router 5. Let's create network 10 over here. So router 4 has path A, B, and C to choose out of to go from router 4 to network 10 through router 5. So path A is through router 1, path B is through router 2, and path C is through router 3. So let's calculate the feasible distance of this route. The top path, router 1 is reporting a distance or sending a reported distance of 30 to router 4, and the distance from router 4 to router 1 is 50. So the total distance for path A is 80. Router 2 is reporting a distance of 90 to router 4, and router 4 has a distance of 10 from itself to router 2 for a total distance of 100 for path B. Router 3 is reporting a distance of 70 to router 4, and router 4's distance from itself to router 3 is 40 for a total distance of 110. So, path A becomes your successor route with a feasible distance, an FD of 80. Will path B even make it to the topology table? Well, my feasible distance is 80, and the feasibility condition states that my reported distance must be less than my feasible distance for the route to be installed in the topology table. Over here, router 2 is reporting a distance of 90 to router 4, which is higher than my feasible distance. So path B won't even be considered for installation in the topology table. Why is that? Well, in effect, router 2 is telling router 4 that I'm further away from you to get to router 5. So router 2 is telling router 4 that I'm even further from router 5 than you are, because it is reporting a distance of 90, basically telling router 4, actually, I'm further away from your destination than you are. So if router 4 tries to route to router 2, and if you pick router 2 up and put it further away from router 4 might send information to router 2 and then have to pass back through itself to get to network 10, which would cause a routing loop. So the feasibility condition is a loop prevention mechanism. So on a diagram, it might look like this, but in effect, router 2 is actually further away from network 10 than router 4. This could show up as a test question. Now, let's look at the last route. Even though the total distance is more than path B, path C's total distance is 110, path B's total distance is 100, but the reported distance that router 3 is reporting to router 4 is 70, which is less than your feasible distance. So path C goes into the topology table, and it is your feasible successor route. Now, if the successor route fails, which is path A, the next best feasible successor, which is path C, immediately becomes the successor, which helps with convergence because you already have alternate paths to the same destination stored in your topology table. So if the best path fails, you immediately promote the next best path to the routing table. This concludes the feasibility condition lecture.